Okay, let me just introduce chapter 3, just an introduction. So I haven't uploaded the notes in the e-learning yet, because still looking at which one that I should give as exercise. Okay, but chapter 3 is a vector space. Yeah. So let me write out the definition of a vector space so you can start with that. Okay. Definition 3.1 is a vector space. Okay. Let me get the same, so I don't use a different notation. Okay, let V be a non-empty set with two operations. The two operations is not multiplication and addition, but the operation is addition and multiplication by scalar. Scalar is real number. Yeah? And UVW in V, K1, K, K1, K2 in R. Okay, then V is called a vector space if the following 10 axioms are satisfied. Okay, so V is a vector space if these 10 axioms are satisfied. What are the axioms? Axioms means the properties of the set. U, this is for U, V, W in V. So U plus V is also in V. Okay. You have two elements inside the set. When you add, it is also the element in the set. Number 2. U plus V is V plus U. This one, we call it close under addition. Close is not close. Close means when you add two elements in V, it goes back in V. It didn't go out. Like you have an integer, you add with another integer, you get another integer. It's still the same set, yeah? The one that is not close, as an example, is you have an odd number, you add with another odd number, it becomes even. In that case, it's not close, right? So this is how you check. Okay, the third one is, or this is what we call commutative. Okay, U plus V is equal to V plus U. As numbers, 2 plus 3 is 3 plus 2. As matrix, A plus B is B plus A. Yeah, so as functions, F plus G is G plus F. So the vector space is not necessarily numbers. It can be polynomials, functions, matrices. The third one is it has to be associative. So you take 2 U, V, W in V, any 3. Then when you add, this one is you add just 2, right? This one you take 3 of them, but you add this first, U plus V plus W, or you add this first, it doesn't matter, like numbers. But some sets and some operation does not satisfy this. For example, subtraction, right? If you replace with subtraction, U minus V minus W, this is not equal to U minus V minus W. Because U minus V minus W is U minus V plus W, right? Not U minus V minus W. So this is why you have to check whether the given operation is associative or not. So you have to check one by one by one. Okay. And this is number 3. These are all still addition, yeah? For number 4, okay, so I put here, there exists 0 V in V such that U plus 0 V is U, which is 0 V plus U. What does this mean? Okay, there exists, yeah? You know, E is like this. So if you flip this way, it's still E, right? So you flip the other way. The mirror is the other way. There exists a zero matrix, a zero vector. That's why I put 0 sub little v in V. This is just a symbol, yeah? There exists a zero vector. This is such that U is any vector in the vector space plus that 0 equals U back, okay? And you can add on the right or on the left. For example, if I give you integers, plus or minus 0, plus or 0 and plus, or 0 and all the negative numbers, right? You add 2 integers, you get still an integer, right? Integers 2 plus 3 is 3 plus 2. So integers, they are commutative. Numbers, you can add in each way, right? Associative. What is a number or integer such that when you add to another integer, you get that number back? 2 plus what is 2? Type. 2 plus, so the 0 vector in this set is the number 0. That is how you have to find the 0. We call it the 0 vector. So in this one, 0v is just a number 0. Okay, now look at matrix. Say I have 2 by 2 matrix, yeah? 2 by 2 matrix. Matrix plus matrix is a matrix, right? A matrix plus a matrix is a matrix. A and B. A matrix A plus B is B plus A, right? Matrices are associative. What is the 0 vector? So when we add a matrix to this 0 vector, is that matrix back? What is the 0 vector? This matrix A plus what equals to A? Type. This is my first example. The second example is a matrix. Can be any matrix. The 0 matrix. Yeah, the 0 matrix, you add any A, a matrix, to a 0 matrix, you get A back. All right, so these are the first 4. Number 5. Number 5. For all U in V, there exists minus U in V such that u plus negative u is 0. And what we call is the negative vector. Negative vector. Thanks. Okay. You have to get the 0 vector first before you find the negative vector. Let me repeat. For all, terbalik pula kan? That exists. For all u in V, for any element in this V, there exists what we call the negative u in V, such that u plus its negative equal to the 0 vector that we found in number 4. Right? So as of for the example, integers, if I give you 3, what do you add 3 with to get 0? 3 plus what is 0? Negative 3. And negative 3 is also an integer. Yeah? So 3, negative 3. If I give you negative 5, what is the negative of negative 5 when I add to be 0, which is 5. Okay? That is for Z. If I give you this set, Z plus 1, 2, 3, 4, and so on. Is it a vector space? Then you have to check one by one. I haven't finished yet. This is only halfway. We have another 5. Okay? This is not because why? Positive plus positive is positive, yes. U plus V is V plus U, yes. Positive number, you can commute. Associativity, yes, it's true for numbers. Is there a 0? It is close. It is close under addition. Because positive number plus positive number is a positive number. Eugene, this is close under addition. But it has no 0, right? It has no 0. Okay, let me add 0. I call this union 0. So I add 0. Okay. Now, is it a vector space? I cannot ask that because it's not 10 yet, but does it satisfy all 5? Yes or no? Why not? Still no, because if I give you 3, what do you add 3 with to get 0? 3 plus what is 0? Negative 3, right? But negative 3 is not inside here. So there is no negative. We don't call this yet inverse, but it's the inverse for under addition. Don't get confused with the inverse under multiplication, right? But yeah, we call this also inverse. This is called inverse, but under addition. There is no inverse for this part because there is no negative numbers. So that's why I said earlier that in chapter 3, you have to think first before you write your answer. Because sometimes the answer is just short. You don't need to go one. You just think first, okay? Then you think about which one that it does not satisfy. Okay, we have to take a break. What time is it now? 12:01. So we come back at 12:10, yeah? Okay. So number 6. Remember, I put U, V, W in V, K, K1, K2 in R. So do I use K just now? In the notes, I use C, but it's okay. I normally use K, but you can use also C, like in the notes, C times U. So that means if U is in V, the multiple is also in V. Yeah. And remember, this K is a real number. So it can be positive, negative, fraction, anything, any real number. So if I give you something like Z, okay, we say this one is closed under multiplication by scalar. Now my question is, integers, is it closed under multiplication by scalar? Yes or no? Yes or no? Yes, no. Yeah, the answer is no, because if I take 2 in Z, if I take 1/4 in R, this is the C, this is the U, CU is 1/2, right? And 1/2 is not in V. Okay, so it is not closed under multiplication by scalar. If you have V there, if you have U, V in here, U plus V also have to be in there to be closed under addition. And KU or CU has to be also inside, cannot go out. Okay, so if I change this to, if I change this to R, then it is closed, yeah, under multiplication by scalar, because real number times real number is still inside R, a real number. Okay. Okay. Or if I said 2Z, if V is 2Z, even integers, yeah, even integers. Okay, it is closed under addition, because even plus even is even, right? U plus V is V plus U, because it's just numbers. Associative, yeah, U plus V plus W, associative. 0, yeah, because 0 is even, 0 is inside. Negative or inverse, yes, because negative of the evens, they are all the negative evens, yes. But if you multiply a real even number like 6 by any real number, do you get again the even integer? We're not multiplying by integer, we're multiplying by a real number. So suppose U is 4, C, K, I use this one, K. This is the C, is the K. K is 1/8, right? So KU is half. This is not in V. Still, it's not a vector space. Okay. Number 7. Number 7. Okay, let me start by following the notes by C. Yeah? CU plus V is CU plus CB. These are vectors. this is a number, real number. As usual, C plus DU is CU plus DU. You know, some operation, if they change the operation, this might not be true. So in a weird, not normal operation, you have to check whether this is true or not. So the question can change. Okay, you might be thinking like, okay, if you multiply, this is normal for numbers. Of course, this is true. But sometimes the question is changed. The operation is also changed. So CD is in area. CDU is CDU. Also multiplication, you can change the parentheses. Last one is 1 as number 1, real number 1, times U. U is the vector space. The vector, sorry, is equal to U. You might be thinking like, of course, 1 times U is U. But sometimes the operation multiplication is also changed to not the regular one. So in that case, you have to check whether this applies or not. So I have put number 1 until number 10, the axioms. Yeah, the axioms. Okay, let's look at some examples. What time is it? Okay, I have 5 minutes before I give you the question, and then I let you answer the quiz. Okay. So I have given you these examples. Yeah, this satisfies all. The second one is R2. And R2 is a pair such that X and Y is, this is the XY axis. So any 2 XY, you add another 2 XY, it will be also in XY. And the 0 will be 0, 0, right? 0, 0. And the negative of, if U is XY like this, the negative will be negative X, negative, right? And C times, if this is U, C times U is the multiple there or multiple down here. Okay. And then you have R3, X, Y, Z. Dot, dot, dot. You have Rn, in which you have n component. N component. I can give you 3, 4, 10, 20, 200. They are still a vector space. Next one is the matrix. I already mentioned to you about the matrices. It can be any rectangle, not necessarily square, yeah. We can also put complex number. So complex number is a set of x plus iy, xy reals. Because complex number plus complex number is a complex number. And once it's number with a regular addition and multiplication by scalar, you have that property satisfied. The 0 is just 0 because 0 is 0 plus I0, right? The negative is just negative x minus IY. So this is okay. Next is polynomial. Polynomial plus polynomial is a polynomial. Zero polynomial is just 0, it's a polynomial. You know how to write the polynomial? P of n is an x n, an minus 1. Polynomial, the AI can be any real number, and n here is, oops, and here is a power. This is x to the 0, right? Actually. So this is because some authors n include 0, some does not include 0. So this is, I better use like this. The coefficient, they can be any real number. The power has to be non-negative. 0, 1, 2, 3. Like px equal 2x cubed minus 3x squared plus 1. That is a polynomial. You learned this before, right? So this is a vector space, and the 0 is a 0 polynomial. Okay. Number 8. Number 8 is here. F. A continuous function. F is a continuous function. Who remember the definition of a continuous function? You learn in calculus or calculus 1 or high school or secondary school. A function is continuous at a point A if the limit of fx is the same as the value of the function at that point. Yeah. So a function is continuous at a point. You have 3 conditions, right? That is the left limit equal to the right limit, which is equal to the limit. And the function is defined at that point, FC, and they are equal. Okay, that's, if you forget, go back and find the definition using set. So this is actually a vector space, because a function add to another continuous is still continuous. Okay, so I will leave you today with the 10 axioms. Your homework will be to read through, hopefully, the first part of the notes can be uploaded in the e-learning by weekend, right? So you can read through before next class. We will go to more examples. The one that have the book, you can read the whole chapter if you want, but just finish the first 2 sections until subspace, okay? Then you will see whether you understand without going to class just by reading. If everything is so clear already, it's good. If not, then you see when I have explained, then whether you can understand that or not. All right. Okay, I will stop here.